It was one of the great dilemmas of semiconductor manufacturing history, and each of the big semiconductor makers had to decide for themselves, gate first or gate last. What does it mean? Well, in this video we dive into another spectacular piece of semiconductor lore. But first, this is a reminder that this video is brought to you by the Asianometry Patreon. Early access members get to see new videos first, blah blah blah. You know the pitch. Subscribe, really appreciate it. Thank you. So I covered some of this in prior videos, so just the basics here. A metal oxide field effect transistor, or MOSFET, is a tiny piece of chemically altered silicon that can switch between a conducting and non-conducting state. It has four major parts, the first three of which are the gate, source, and drain. The source and the drain are regions of silicon doped with other elements to donate or receive electrons or electron holes. When you activate the gate with enough voltage, it creates an electric field that attracts electrons or electron holes up from the semiconductor. And this creates a conducting layer between the source and the drain, the channel. On top of the channel is the fourth, but very important part. It is a thin, very pure film of oxide that we call the gate dielectric, or gate oxide. The gate oxide's job is to help create the electric fields that open the gate. It's very thin compared to the rest of the transistor, typically 50 to even just 5 nanometers thick, and this makes it one of the most challenging parts of the transistor to manufacture and shrink. This gate and its oxide are the heroes of our story today. At the rising dawn of MOS silicon in the late 1960s, we made the gate from aluminium metal, and for the gate oxide we used silicon dioxide. This explains the origin of the name. MOS stands for metal oxide semiconductor transistor. Unfortunately, using aluminium caused problems. To create the source and the drain, we had to heat the wafer to temperatures of 1000 degrees Celsius or more. The process is known as diffusion. The problem is that aluminium melts at 660 degrees Celsius. So manufacturers had to diffuse the source and the drain before they produced the gate. So in other words, the gate was done last. So manufacturers had to align this aluminium gate so that it is right on top of the micrometer-sized channel. Doing this consistently was hard and caused errors. Errors caused the MOS transistor to short out or consume excess power. So the brilliant thing Fairchild, Intel, and several other manufacturers did was to replace the aluminium with heavily doped polysilicon. Now we can do the gate first, and then use it as a reference to properly align the source and drain. This was called self-aligned polysilicon gate technology, and the method aided the eventual success of the MOS transistor. And for the next 40 years, the polysilicon gate and the gate first sequence remained at the very core of mainstream semiconductor manufacturing. The first MOSFET device was about 20 micrometers large. Its gate oxide was about 100 to 150 nanometers thick. But as we put more transistors on an integrated circuit, we shrank their physical dimensions and parts, including the thickness of the gate oxide. The industry uses a term to measure this called equivalent oxide thickness, or EOT, which is 1 G away from an EGOT. This shrinkage was most aggressive in the late 1990s and early 2000s, thanks in part to big gains in lithography. By 2001, we had the 130 nanometer, or 0.13 micron node, and in that node, the channel was just 70 nanometers long, and the gate oxide only about 20 to 25 nanometers thick. It was at this node that people started noticing a problem: short channel effects. These are when the electric fields coming out from the source and drain encroach onto the electric field coming from the gate, weakening its influence and control over the channel. As a result, electrons jump over the gate when they are not supposed to. This causes leakage, meaning unwanted current flow and excessive power consumption. The semiconductor industry is conservative. Billions have already been spent on existing equipment, so R&D labs needed to find a solution that would not majorly affect the existing process flow. After 130 nanometers, we had the 90 nanometer process node, scheduled for early 2004. Here, the MOSFET channel would be shortened to a length of 45 to 50 nanometers. The gate oxide just about 1 nanometer thick. In 2002, Intel, then unquestionably the most powerful semiconductor company in the world, shocked the industry by announcing that they would add strained silicon to their process. This is where you add layers of quote-unquote strained silicon to the channel. Strained silicon is called that because the silicon's crystal atom structure, its lattice, has been stretched beyond its normal distance, like the threads of a fabric being pulled apart just slightly so. Essentially speaking, electrons and electron holes can travel faster through strained silicon than they can through traditional silicon. This has been known since the 1950s. So adding strained silicon to the channel lets the transistor somewhat overcome negative short channel effects. IBM and the rest of the industry had been developing strained silicon for several years now, but they scheduled it for the 65nm node, not the 90nm node, so Intel jumped the gun by a full generation. Intel presented a slick way of straining the silicon. A CMOS is made up of a P MOSFET and an N MOSFET pair. It's what the C stands for, complementary. The P and N monikers are tied to the type of charge carriers running through the channel of the particular MOSFET. Intel used different methods to introduce strained silicon to the P and N MOSFETs. For the P MOSFET, they etched a trench near the transistor's gates and filled it with silicon germanium using a method called epitaxial CVD. Germanium's atoms are slightly further away from each other than silicon's. In other words, germanium has a slightly larger lattice constant than silicon. So depending on how you mix silicon and germanium together, you can modify a lattice constant. So, depositing a strain-inducing layer of silicon germanium onto silicon creates what is called a lattice mismatch. This mismatch will quote-unquote compress the neighboring patch of silicon in a certain direction. To stress the N MOSFET, the other transistor, Intel adds another layer of silicon nitride on top of the whole transistor. This creates tension, which again strains the silicon in the channel. Note that the strain goes in opposite directions for the N MOSFET and P MOSFET. The P MOSFET, a compression or squeezing in, and the N MOSFET, a tension or pulling out. Anyway, Intel claimed in their press release that this strained silicon technology would be relatively easy to introduce into the process flow, just 2% of their wafer cost. But considering that they were also introducing another very complicated thing at the same time, low-K dielectric, which involves the interconnects, and I have a whole nother video on that, it was a whole lot at once. Thusly, Intel's 90nm node ramped slowly. Products like the Pentium 4 Prescott were delayed a few months. And even after the release, the chips did not show massive performance gains and suffered some thermal issues, though most observers attributed these to the chip's ambitious design rather than the node. Strained silicon, by the way, remains a core part of the semiconductor technology palette, so don't forget it. After the 90nm node, we had the 45nm node, and it is one of the most famous in silicon history. This node would ramp up in the mid-2000s at about the start of the smartphone revolution. Mobile phone chips have to be power efficient, so it was imperative for Intel and the rest of the semiconductor industry to fix these power leakage problems. The planar transistor gate's effectiveness depends on its capacitance. The value of that capacitance is represented by the following formula. C equals K, or dielectric constant, times E times area, divided by thickness of gate oxide. Let us break down the equation starting with area. The area refers to the surface area of the gate itself. With the new node, it is, of course, getting smaller. Unless something changes, that would shrink the capacitance value and weaken the gate even more. But what can we raise? E refers to the permittivity of free space. Its value is a fundamental, universal constant in electromagnetism, so it's not changing. And in the denominator, the gate oxide's thickness cannot be shrunk any further. Right now, the oxide is just 1.2 nanometers thick, or about the width of 11 hydrogen atoms. There is simply nowhere to go. Thus, the only remaining factor is the dielectric constant, or K. K refers to a material's ability to concentrate an electric field. The higher the K, the more capacitance it can provide. So gate oxide with twice the K can draw twice as much charge into the transistor channel, improving performance and cutting leakage. Integrated circuits use materials of varying K values. For instance, a material of a low K value is used for insulation for the interconnects. Lower K is good here because we do not want electric fields in one wire interfering with a neighboring wire. But raising K means shifting away from silicon dioxide for the gate oxide. For the 130 nanometer node, they played around with introducing nitrogen to the silicon dioxide, creating silicon oxynitride, and it kind of worked, but that was a very small and conservative step. Entirely changing the oxide was a whole nother beast, and no small trifle. Silicon dioxide literally created Silicon Valley. As a semiconductor, silicon itself was just okay. Its killer app was silicon dioxide. We're tampering with 40 years of silicon engineering, but that is exactly what Intel was about to do. Starting around 2000, the industry started researching a variety of possible replacements. Intel itself cycled through several high-K gate oxides, from titanium dioxide to hafnium silicate to zirconium silicate, and they would build sandwiches of the materials and charge them up in an attempt to measure the K value. One promising gate oxide material was hafnium oxide. It not only had a very high dielectric constant, around 20 to 25, but it was also quite stable at high temperatures and did not react negatively with the silicon substrate. Intel discovered that if you deposited it precisely right, it worked as a gate oxide. This deposition precision, done at an atomic layer, can be achieved using a newly commercialized technology, atomic layer deposition. But there was a catch. You could not simply swap out the existing silicon dioxide with hafnium oxide because it reacts with the polysilicon gate at high temperatures. So how do we deal with that? Companies came up with a variety of ways to handle this problem. Two became prominent with their own backers. One method that came up involved us inserting a very thin metal layer of titanium nitride on top of the new hafnium oxide gate oxide. You would then put the polysilicon gate over on top of that, plus a layer of a metal silicon compound called a silicide for reducing contact resistance. Once all that is done, you can then go create the source and the drain, where high temperatures of about 1000 degrees Celsius are used to activate dopants. Anyway, the idea of inserting this metal layer into the gate stack was called the Metal Inserted Polysilicon Structure, or MIPS. And since we build the gate before we put it through those high temperatures, the industry referred to it as the gate-first integration option. The ideas behind gate-first came from Sematech and the IBM Research Alliance, which included IBM, Chartered Semiconductor, Samsung, and a bunch of other guys. They were its primary champions. But Intel decided upon something very different to tackle this problem. In this method, we first use ALD to deposit a nanometer thick layer of hafnium oxide, gate oxide. After that, we build a polysilicon gate over it like as usual, and we use that polysilicon gate to align and produce the source and drain. This is all the same as the aforementioned gate first method. But after that, we destroy the gate by either removing some or all of its materials. Then we rebuild it by depositing metals like aluminium into the resulting hole, like putting a filling into a cavity. Furthermore, different recipes need be implemented for NMOS and PMOS transistors. Remember, CMOS has both. Yes, this is all very complex. Because the final gate is built at the very end, after all the source/drain and high temperature processes are completed, the industry took to calling it gate last. Way later down the line, in 2009, Intel produced a second generation of this, where they redeposited the high K gate oxide layer all over again, and they named it high K last. So we got to call this gate last, high K last. Whew. The primary philosophical difference between gate first and gate last is whether or not we want to keep the first polysilicon gate. Those in favor of going gate first argue that their method was simpler and largely sticks to the old flow, just like the 130 nanometer node's way of adding nitrogen to the silicon dioxide gate oxide. It would be simple to integrate. On the other hand, Intel's gate last method raised wafer costs by about 4% due to the introduction of several new challenging process steps. For instance, they used chemical mechanical polishing, or CMP, essentially a big grinder, to grind the gate down. Adding this CMP step also means several new design rule checks for designers, which is 麻烦. Plus, there was a density penalty of about 10%. Yet at the same time, gate first suffered the fundamental risk that the high temperature steps associated with producing the source and drain would damage the gate's long-term integrity. Intel nevertheless moved forward. In the second half of 2007, their two major fabs in Oregon and Chandler, Arizona, began high-volume production on 45 nanometer Penryn chips. They were first in the industry with high K, and it became one of their highest yielding processes. It's interesting that Intel's work with these new materials delayed their introduction of 193 nanometer immersion lithography tools. They stayed dry for the 45 nanometer node, not adopting it until the next node, 32 nanometers. Side note, I am immensely amused to read reports in 2006 of Intel, quote-unquote, hoping to use EUV for their 32 nanometer node. Alas. Intel co-founder Gordon Moore embraced all this new complexity. While promoting the new node, he called it the, quote, biggest change in transistor technology since the introduction of polysilicon gate MOS transistors in the late 1960s, end quote. At this time, TSMC was the leading foundry. For their 45 nanometer node, TSMC decided to focus on integrating 193 nanometer immersion, or just 193i, lithography technology. So instead of high K, they used what they called triple gate oxide. 193i took longer than TSMC expected, so much so that sometime in 2009 they essentially relabeled it to 40 nanometers. Perhaps they did this because SMIC had recently just announced the 45 nanometer node too. I told you that these names were always just marketing. Since Intel was doing its own thing back then, them having high K was not largely a competitive threat. But the IBM alliance included several foundries, IBM, Samsung, Chartered, STMicro, so their high K gate technology was a threat. In April 2008, the IBM Alliance partners announced that their high K metal gate process with gate first would be included in their 32 nanometer node. Moreover, they were starting to open that up for their design customers. The announcement happened just a week before TSMC's 2008 Technology Symposium and was an obvious challenge. At the symposium, CEO Rick Tai announced that TSMC would incorporate high K metal gates into the high-performance variant of their 32 nanometer node using gate-first method. Intel shipped products with their high K metal gate nodes with minimal delays. They even brought out their aforementioned second generation of their gate last before anyone else did. Chips with the Penryn and then Nehalem microarchitectures hit the market with largely no problems. Meanwhile, TSMC flubbed its 40 nanometer ramp, hitting the market sometime in Q1 2009 or about a year late. NVIDIA produces GeForce 100 series on this node, and the latter's struggles caused the former to be delayed for a while. Despite these issues, TSMC eventually got it to work, though not before Rick Tai lost his job, and 40 nanometer became a core node. In early 2012, it was 32% of company revenues. Even over a decade later, it still brought in 5 to 6% of TSMC's 2023 revenues, making just that business line alone roughly over twice the size of Tower Semiconductor. The 32 nanometer process descended from that 40 nanometer node, but it apparently did not yield, so much so that TSMC killed that node entirely. Their focus shifted to the 28 nanometer or N28 process node. In classic TSMC style, they ran both the gate first and gate last versions of that node in parallel. They then announced in February 2010 that they chose to go with gate last. SVP of R&D Dr. Zhang Xiangyi, who also returned to TSMC when Morris Chang retook the CEO spot, later explained that despite the additional process complexity, gate last was better. It let them use different metals for the NMOS and PMOS, and because of that, they can adjust both transistors' threshold voltages, which grants more design flexibility for customers. Chairman Morris Chang later added, I do believe the gate-first people will change to gate-last at the 22 nanometer node. I'm not criticizing them, but I think they will change. Unless they can find some very innovative way to adjust the threshold voltage without a lot of high cost, they will have to change. As always, Morris Chang was right. The gate-first people struggle with ensuring the stability and reliability of the metal gate after thermal processes. As time passed without new chips, people's arguments about why gate-first over gate-last became increasingly outmoded. For instance, the aforementioned design rule checks due to CMP had to be implemented anyway in the next node due to lithography constraints. Samsung had recently entered the logic foundry business. In 2010, they were aggressively building capacity and courting customers. They wanted to distinguish themselves as leaders with shiny, bleeding-edge technology. So they were an early adopter of gate first, using it for their 32 nanometer and 28 nanometer nodes. but quietly behind the scenes they spun up an R&D team to research gate last for their 22nm node. As doubts mounted, IBM and GlobalFoundries publicly backed gate first. When financial analysts began reporting rumors of technical issues, they pushed back, investing a lot of their credibility in doing so. But finally, in 2011, they waved the white flag and switched to gate last technology for their 20nm node generations. Samsung as well. By then, TSMC's 28nm node had entered the market and smoothly ramped up throughout 2012, basically winning the 28nm foundry market. N28's home run success meant a record financial year for TSMC. N28 unifies every trick in the book: high-K metal gate, 4th generation strained silicon, 193nm immersion lithography, and copper interconnect with low-K dielectric. I consider it the pinnacle of planar transistor technology, and it remains one of TSMC's most successful nodes. The whole story of the high-K transition demonstrates the challenge of competing in semiconductors. The gate-first people could have made the method work eventually, if they had the time. But in 2011, Intel announced their historic move to FinFET. Suddenly, IBM and everyone else in the industry still ramping up the high-K metal gate was old news. They must have felt the necessity to move on. High-K remains a core part of Intel's lore of innovation. They still call back to it as a shining example of their technological prowess. And rightfully so. The whole thing was a masterfully conducted symphony of all of Intel's strengths: incredible insight into the nanoscale behavior of exotic materials, brutal execution and global scaling, the absolute crushing and lapping of competition. Moreover, they didn't just rest on their laurels. 3 years after breaking the league, they were again hurtling onwards to FinFET. It's remarkable just how ahead Intel was of everyone else during this time. Such an amazing lead, so quickly squandered. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.